Hello everyone. In this video, we'll take a look at how to create a minimum spanning tree of a graph using Kruskal's algorithm with disjoint set union data structure and path compression technique. So just to quickly revise, what is a minimum spanning tree? So in simplest terms, a minimum spanning tree is a subset or subgraph of a graph that connects all the vertices together without any cycles. So because it connects without any cycles, it's a tree. Because it connects all the vertices, it's a spanning tree. And additionally, the total weight of the edges in the tree is as low as possible. Therefore, it's a minimum spanning tree. Okay. So this is how the graph has been given as input. We have 5 vertices and 7 edges. These are the 5 vertices. And now the edges are edge between 1 and 2 with the weight 3, edge between 1 and 3 with the weight 1, edge between 1 and 4 with the weight 5, edge between 2 and 3 with the weight 2, edge between 2 and 5 with the weight 3, edge between 3 and 4 with the weight 2, and edge between 4 and 5 with the weight 4. Now we'll apply the Kruskal's algorithm on it, but a prerequisite for that is we have to sort the edges by weight. So we have sorted the edges in the non-decreasing order of their weights. You can take a look and verify the same. Now let's actually begin with the Kruskal's algorithm. Now the data structures that you see over here, which look like an array, is called as the union find data structure. It is also called as the disjoint set data structure. Okay, now we have all the vertices, and for each vertex we have a parent or a representative. Okay, now for initialization, we set each vertex to have the vertex itself as the parent or representative. This means that every vertex is in its own connected component, own separate component initially. Okay, so in Kruskal's algorithm, we always form a forest. Okay, so therefore, our forest initially consists of every vertex or every node in its own component. Okay, so that is what this means. Now, let's try to add the first edge. Here we perform the find operation. Find operation checks both the endpoints of the edge. It finds out the parent or representative of both the endpoints. If the parent or representative of both the endpoints is the same, then there is a cycle. And like in this case, if the parent or representative of both the vertices 1 and 3, if the representatives or parents are different, that means there is no cycle. Therefore, we can go ahead and safely add that edge to the tree. So let's do that. Now, when you add the edge to the tree, or more strictly speaking, to the forest, because crystals may result in a forest, and that forest ultimately gets connected to form a tree. So when we are adding the edge to the forest, we also have to do two more operations. That is, we have to perform union. We have to perform union. Now, what does union mean? Union means that now you are taking the union of these two sets. Okay, we can imagine each vertex initially to be in its own connected component, or we can say that each vertex is in its own set. And when we perform union, we perform a union of these sets, or we connect these connected components together. So we are connecting the component 1 with component 3, and together they are one component. And because they are one component, they will be represented by one of them, that is in this case 3, let's say. Okay, so 3 will represent the connected component which is formed by the union of 1 and 3. Okay, now next step is you also have to calculate the total weight, because you just added an edge of weight 1, the total weight becomes 1. Okay, note that this graph is an undirected graph, and the basic principle of Kruskal's algorithm works only for undirected graph. Minimum spanning tree is defined for undirected graphs. In case you have a directed graph, you get something called as an arborescence and minimum spanning arborescence, which is not the topic of this video. Here we are forming minimum spanning tree, and it works only for an undirected graph. Okay, now what I have drawn over here is just a representation to show that the parent or representative of 1 is 3. Let's move ahead. Let's try adding the second edge. So the second edge is between 2 and 3 with the weight 2. Who is the parent of 2 or representative of 2? 2 itself. Parent of 3 is 3 itself. Their parents are not the same, so therefore there will be no cycle and we can safely add that edge. When we add that edge, we'll perform union. So now 2 and 3 will be in the same connected component and their representative will be 3. So now effectively 1, 2 and 3 are in the same connected component and their representative is 3. Also the weight will be updated to 3. Okay. So this is after adding the second edge. Now let's try adding the third edge. The parent or representative of 3 is 3. Parent or representative of 4 is 4. Therefore, they are in separate components, you can say. Therefore, you can add the edge 3, 4 to the uh, forest that we are forming. Okay. So, parent 3 is 3, parent 4 is 4. They are not the same, so no cycle. So, we can add the edge to our answer. Okay. And total weight will also get updated to 5. We'll perform union. Now, when we perform union over here, when we add the edge 3 to 4, so this is what is happening right now. Till now, what do you have? You had 3, 1, 2. Now, when you're adding 3, when the representative of your current parent node or current representative changes, okay, so basically you are performing a union of this component with this component. So, parent of 3 becomes 4, okay. So we could add the edge 3 comma 4 comma 2 because there is no cycle. So we go ahead and add that edge and we update parent of 3 equal to 4 and we also update the total weight to 5. Okay, so that is done. Now when we try to add the edge 1 comma 2, I will again draw this, okay, to remind you what is happening over here. If you take a look at the disjoint set data structure right now, the parents of 1 and 2 are 3. So as it is, they are in the same connected component. Okay, so it will form a cycle. However, since the parent of 3 is 4, now when you are considering the nodes 1 and 2 or vertices 1 and 2, you will actually check whether their parent also has some parent or their representative also has some representative, which is true in this case, which is 4. So therefore, find will perform parent of 1 equal to 3, but parent of 3 is equal to 4. Therefore, parent and parent of 4 equal to 4. Going one level ahead, parent of 4 equal to 4. Even in the previous slides, when we did, let's say, parent of 1 is whatever 3 in the previous slides, implicitly there is one more step like parent of 3 is 3. So similarly here, parent of 1 is 3, parent of 3 is 4, and parent of 4 is 4. So what do you have to do? We perform something called as path compression. So what happens is instead of having this complete uh, hierarchy, okay, I'll just cut this. Okay, instead of having this complete hierarchy, okay, by path compression, what we do is we directly make 4 as the parent of 1 and 2 as well. So this is path compression because instead of having a path of length 2, you directly have a path of length 1. And although this may not matter in this small example of 5 vertices, when you have hundreds of thousands of vertices or millions of vertices, it matters a lot. Okay. And another thing is we perform it in a lazy manner. That also matters. Okay. So, for example, when we updated the parent or representative of 3 to be 4, we did not immediately go ahead and check all other nodes which have the parent as 3. We don't do it immediately. We perform it in a lazy manner so that now when we are actually performing um, find operation on 1 and 2, we found their parent is 3. Then we check whether the parent of 3 is some other node, etc. So we perform it in a lazy manner. Only when it is needed, you do the path compression. Okay, so this matters on large graphs. Okay, this optimization matters. Okay, so now edge 1 comma 2, we checked for 1. Similarly, we'll check for 2. So parent of 2 is 3, parent of 3 is 4, and parent of 4 is also 4. So by path compression, parent of 2 will be 4. So ultimately, you can say that the parent of 1 and 2 both are 4 in this case. Okay, therefore there is a cycle. Okay, and because there is a cycle, you cannot add this edge to the forest or the answer or your minimum spanning tree. Okay, let's move ahead to the next edge. Edge is 2 comma 5 comma 3. Parent of 2 is 4. Parent of 5 is 5. So you can add this tree. Oh, sorry, you can add this edge to your forest or to your minimum spanning tree. Okay, there is no cycle. Okay, now what it will look like? 4 to 5. So now parent of 4 will get modified. Okay, parent of 4 will become 5. So effectively, what is happening? 5, 4, 1, 2, and we have, sorry, 3, not 1 2 directly over here, 3, and then you have 1 and 2, and we have performed path compression from 1 and 2 to 4. Okay, so now when you're considering for 2 comma 5, we are done, we perform union and all. When we consider the next edge, okay, total weight also gets updated. Also keep a track of total weight. Total weight also gets updated. Now when you're considering the next edge, that is 4 comma 5, now both of them have the same parent 5, same representative 5, so they cannot be added. There is a cycle. Let's go to the last one, and here again you will see an instance of path compression. Okay, so 5, 4, 3, 1, 2. Path compression till now was only up to 4. Okay, and now when we are finding the parent of 1, again we'll do the same thing. So parent of 1 is 5 now because of path compression. That is, when we are checking for parent of 1, okay, we'll see that parent of 1 is 4, parent of 4 is 5, and parent of 5 is 5. So therefore, we'll perform this new path compression, that is parent of 1 is 5. Do we change it for 3 or 2 as of yet? No, because that was not a part of our query, the find query. Okay, so we only perform it lazily when it is required. Okay, so we update only the parent of 1. Okay, and because parent of 1 is equal to parent of 4, there is a cycle. Okay, it should be parent of 4, not parent of 5. Okay, parent of 1 is equal to parent of 4, therefore there is a cycle, and therefore we cannot add this edge. We have performed path compression as well. So finally all the edges have been considered, so total weight is 8. Okay, so finally this is our answer. Okay, now time and space complexity consideration. The time complexity can be broken down into three main steps. On these main steps, first is sorting the edges. So sorting, because there are e number of edges, so it will take e log e time. Okay, because sorting takes n log n. Second step is disjoint set operations. For each edge, we perform up to two disjoint set union operation. That is find and union. Okay, so effectively, actually speaking, technically speaking, it is alpha v times e, where alpha v is Ackermann's function. Okay, Ackermann's function, but most of the times its value is close to 4. So this will be, because sometimes when you're performing find, you will have to also perform path compression. Okay, so considering that, it is almost of the order of 4 times e, but it doesn't matter, 2 times e or 4 times e, it will be some constant factor multiplied by e. Okay, so we'll consider it as order of e. Okay, overall time complexity is order of e log e. Okay, and because E is order of V square. That is, if it's a completely connected graph, then number of edges will be V into V minus 1 divided by 2, which is order of V square. We can substitute it over here. Okay. So we can also say that log E is approximately 2 times log V. Okay. So therefore, we can say that time complexity is also O of E log V. Okay. So you can either say that it is E log E or E log V. And about space complexity, you have to store all the edges because you have to sort them, store them, sort them. So therefore, we have to use O of E space for that. And for maintaining the disjoint set data structure that we saw just now, we'll have to maintain an array of size V. Okay, so therefore O of V. So the space complexity O of E plus V. Okay, so that's it for this video. I hope the concept of Kruskal's algorithm, disjoint set union, and path compression was clear to you. If you have any questions, any doubts, do post them in the comments below. Thanks for watching.